Okay, so last time, remember, we introduced the theory of the Fourier transform, and then after discussing some properties of this tool, we began discussing how we can use the Fourier transform to solve different partial differential equations, or at least how to use it to aid in the solution for various partial differential equations. And in particular, we looked at an application to the Dirichlet boundary value problem for Laplace's equation in the upper half plane. And so today I'm going to begin by elaborating a little bit more on this problem. And then in the second part of the lecture, we're going to discuss how to use the Fourier transform to study the Schrodinger equation from quantum physics. And so just briefly remembering, well, what is the Dirichlet problem for Laplace equation in the upper half plane? Well, so we're looking at the equation Laplacian of u is equal to 0 in 2 dimensions. And so our domain is going to be the upper half plane, which is all points x, y with y positive, right? So domain consists of x, y with y positive. And so the reason why we have to use the Fourier transform in this case, and we couldn't use like some of the separation of variables techniques we had seen earlier, is that while in the x domain on the x-axis, right, we're allowing x to range over the whole real line, right? And so the previous techniques we had, for example, using Fourier series, only worked on a bounded interval for x, but now we want an infinite interval for x. And so the previous separation of variables methods we spent a lot of time talking about don't quite work in this setting. And so instead we can use the Fourier transform. Right, and so this is actually, I mean, it's not just, we're not just trying to find a function which is harmonic in this domain. We're looking at a certain boundary value problem associated to this equation. And so we want to assume that when y is equal to 0, u is equal to some given function f of x, right? So this is like the boundary data which will determine the solution. Right, and so we saw that, so I guess this is a theorem. Using the Fourier transform, we derived the following solution formula. So u of xy is given by 1 over 2 pi times integral from minus infinity to infinity of the Fourier transform of the initial data f times e to the minus absolute value of cy. Well, c is like the frequencies which we'll be integrating here, times e to the ix c dx. Right. And so, as with a lot of examples we've seen throughout the course, this is not really like even if I give you a particular function f, it's not really obvious how one would compute this as like a closed form solution that doesn't involve an integral or a Fourier transform. But this is at least a place to start, right? This is some formula which we proved is the solution to this boundary value problem. One thing I didn't mention, just because we were running out of time, we have to, technically we want to verify that this boundary condition actually holds, right? So when y is equal to 0, is u of x comma 0, if we define it by this formula, actually equal to the function f, right? And so, well, let's just check this, right? So it's going to turn out that this is going to be a consequence of the Fourier inversion formula. So if I look at u of x comma 0, this is given by 1 over 2 pi integral from minus infinity to infinity f hat of c. Well, when I set y equals 0, the first exponential term vanishes, right? Because e to the 0 is 1. And so I just have e to the ix c dx. But this is just this term here is equal to f, because this is really just the statement of what we call the Fourier inversion formula or the Fourier inversion theorem, right? So this is just equal to f of x. Right, and so in fact, I mean, we use the Fourier inversion theorem to get this formula to begin with, and so here we're using it again to just check that the initial condition is actually satisfied. Right, and so, well, for a lot of purposes, it's nice to have this formula, but maybe the Fourier transform of the initial state or the initial data f is hard to calculate. Is there a way to simplify this formula a little bit, maybe to get something that involves the original function f rather than its Fourier transform? And it turns out that this is the case, and so this is what I want to discuss now. And so we're going to study something which is called the Poisson formula, which is going to be a version of this formula, but without the Fourier transform. So we're going to replace the Fourier transform by f and try to write the solution in that way. Right, and well, we had already calculated, or sorry, we had already encountered something that I called the Poisson formula a few lectures ago. So this is the Poisson formula for the upper half plane. The previous formula we had was for disks in the plane, right? And so we're not looking at disks anymore. We're looking at the whole upper half plane, right? So it's a different formula, but it's related, and there's some similar ideas that go into the proof. Okay, and so the idea is, well, by Fourier inversion, again, well, we can write. Actually, sorry, this is not Fourier inversion. This is just the definition of the Fourier transform. Well, we can write the Fourier transform of f xc as the integral from minus infinity to infinity of, say, f of z. The reason why I'm using z as the integration variable is just because we have a u of xy, so I don't want to confuse z with x or y. So f of z times e to the minus I z c dz. Right, so this is just, again, this is just the Fourier transform, but I'm using z as my integration variable instead. This is just definition. And so what I'm going to do now is plug it in to our solution formula right over here. And so plugging it in, we get u of xy is equal to 1 over 2 pi times integral from minus infinity to infinity. And then I have another integral from plugging in to replace the Fourier transform. F of z e to the minus I z c dz, and then times everything else, times e to the minus absolute value cy e to the I x c dx. Right? And what I'm going to do now is switch the order of integration, right? So using what's called Fubini's theorem. And so if I rearrange the order of integration here, we can write this as 1 over 2 pi. Well, I'm going to have, I'm going to bring the dz on the outside, right? So I'm going to be able to factor out f of z. And then I have integral from minus infinity to infinity of everything that depends on xi. So I have e to the minus I z xi, e to the minus absolute value xy, and then e to the ix xi dxi, and then integrate with respect to z, right? And so all I did here was, right, I switched the order of, so here I'm integrating with respect to z, and then with respect to xi, I switched the order of integration using the Fubini theorem. And then, well, f only depends on z, so I can factor it out of the inside integral. And then the inside integral, which involves everything depending on xi, is what I have in brackets here. Right. And so while I can simplify this just a little bit, I can write this term here as e to the I times x minus z times xi, and then minus absolute value xy, right? So I just get some exponential term. Well, notice that we're looking at the integral of an exponential, and we know how to integrate just exponentials. The only, at least if the argument is linear. This is not quite linear because we have an absolute value here, but we can break this integral into regions where the absolute value, depending on whether xi is positive or negative, and in each of these regions, we'll actually just be able to calculate this integral, right? And so, right, and in fact, we have this extra 1 over 2 pi floating around. I'm gonna bring this inside, right? So let's bring the 1 over 2 pi in. Just because, I mean, we don't want the 1 over 2 pi just floating around in the formula, we may as well just bring it inside. Right, and so now let's calculate this term in the brackets, right? So now we calculate, well, the inner integral is 1 over 2 pi, integral minus infinity to infinity, e to the I x minus z c minus absolute value xy dx, right? And so the idea here, I'm not going to do all the details because this is just a calculus exercise, which maybe you can pause the lecture and do this for yourself as a good review of some calculus. The idea is we'll break the domain of integration, right? So our domain of integration is the whole real line into, well, I want to break it into two regions, right? Because I need to deal with this absolute value. So I'm going to break it into regions where C is positive and where C is negative. And on both of these regions, I know how to replace this either by plus or minus C, right? Right, so I want to look at regions where C is bigger than 0 and where C is less than or equal to 0, right? So the first is like 0 to integrating from 0 to infinity. And the second, you'll integrate from minus infinity to 0. And if you do this, well, then on each of these regions, you can just replace the absolute value by either plus or minus C, respectively. And then you can just calculate these. You're just looking at the integral of an exponential. And you'll end up getting 1 over 2 pi, 1 over y minus I times x minus z, plus 1 over y plus I times x minus z. Right, each piece is going to correspond to each piece of the integral, right? Each term corresponds to each piece of the integral. Okay, and then if you do a little bit of algebra, you can combine these fractions and then clear the imaginary parts from the denominator. I'm going to skip some of this algebra. Again, it may be a good exercise to review how to manipulate complex numbers, to pause the lecture and check this calculation. But you end up with, this is equal to y over pi times y squared plus x minus z squared, right? And so what you'll do in order to check this, well, you combine these into a single fraction and then multiply by a certain number to clear all the imaginary numbers from the denominator, and this is what you'll end up with. Right. Okay, and so, well, now we've calculated what's in the brackets over here, right? And so now let's just plug this in. Okay, so we haven't actually completely calculated it, but we've at least outlined the steps that you need to calculate this. So therefore, our function u of xy is going to be given by the integral from minus infinity to infinity. Remember, we had f of z. This is our initial data, no longer any Fourier transform, right? It's just the original function multiplied by this other term here. So y over pi times y squared plus x minus z squared dz. Okay. And so this is what's called the Poisson formula for the upper half plane. Right? Right, and so in particular, this gives us a solution formula for the Dirichlet boundary value problem with boundary data f, and there's no Fourier transform anymore, right? So for some functions f, maybe the Fourier transform is hard to calculate, so you can instead use this formula, which involves the original function f rather than its transform. Right. And so this should look very similar to the Poisson formula we had for the disk. It's, in fact, these things, there is a relationship, like a direct connection between these formulas involving some type of transformation, not the Fourier transform, a different type of transformation. But in order to talk about this in more detail, you would need to take a class in complex analysis or complex variables, and you would see why these formulas are in some sense equivalent. But we're not going to go into that today. Great. So I do want to just say a little bit more about this formula, though. So, well, let me just introduce a definition. Let me define a function p sub y of w. Let this equal basically what we have here. So y divided by pi times y squared, but now I'm just going to have w squared, right? So this is the Poisson kernel, right? Which is kind of a very important object that shows up when studying Laplace's equation. And so, well, if we look at the formula we have above, this says that u of xy is given by the integral from -infinity to infinity of f of z times the Poisson kernel sub at y, not at w, but at x minus z dz. Right. And so this expression here should look kind of familiar. Remember, we defined a certain operation called the convolution when we were talking about Fourier series. And so, well, this says that the solution is given as a convolution of the initial data with the Poisson kernel. And so let's just review the definition of convolutions. Right, so the convolution of two functions, say f and g, is defined, right, we had previously defined convolution on a finite interval. The definition on the whole real line is similar. So we have f star g of x. So this star in the middle is usually the notation for convolution. This is the integral from -infinity to infinity of f of z times g of x minus z dz. So this is kind of like, one way to think about this is like a weighted average near the point x of f, right? So maybe g is like concentrated near the point x, for example, or maybe it's not. And so you're kind of weighting f by this near x, right? And so, well, what does this say then? This says that with this definition, the solution formula for the Dirichlet boundary value problem is given by the convolution of the initial data f with this Poisson kernel, right? So that's what this says using this definition, right? And so this is typically one of the ways you'll see the solution formula for this problem written, kind of compactly as convolution with the Poisson kernel. Okay, and so, I mean, just as with the theory of Fourier series, we saw that convolutions are kind of a very important operation for manipulating and working with Fourier series. The same is true for Fourier transforms, although we're not going to spend too much time on this. I do just want to mention we have the following theorem, which should look familiar because we had a homework exercise proving the same thing for Fourier series rather than the Fourier transform. And so the theorem is, well, let's suppose I take the convolution of two functions and I take the Fourier transform of the convolution, right? So notice that this f star g forms a new function of x, right? I have some function f of x and some function g of x, and then I combine them in some way to get a new function of x, right? Which is defined in this way. And so what I'm saying here is, well, look at this function and take the Fourier transform of it as a function of x. And so the theorem is that this Fourier transform is equal to the transform of f times the transform of g, right? So Fourier transform turns convolution into multiplication, right? And so this is one of the reasons why convolutions show up so much when you're manipulating or working with Fourier transforms. And so, well, I'm not gonna prove this, but the proof is similar to the earlier homework problem we had for Fourier. For Fourier series. I mean, you basically just use the definition of, right, you plug in the convolution to the definition of the Fourier transform, and then you switch the order of the integration, and then this will just pop out eventually. Okay. So that's how this is done. Okay, and so that's basically what I wanted to say about this particular problem. I mean, as we've seen many times, and as I've said many times, I mean, this formula is nice because it doesn't have the Fourier transform anymore. So it's maybe a little bit simpler than the first formula we derived, although you're not always going to be able to calculate this integral and get an explicit function, right? You may just have to just deal with the fact that you can't calculate this directly, and maybe you can use a computer to approximate the solution or something like that. Although there will be some examples of functions for which you can calculate this as well, as we saw with like the diffusion equation and some other examples. Okay, and so the next thing I want to talk about now is I want to move on to another application, and so now we're going to discuss some applications of the Fourier transform to the theory of the Schrodinger equation from quantum physics. Right, and so what is the Schrodinger equation? So loosely speaking, this describes the motion of some free atomic particle, right? Right, and so what do we mean by describes? Well, I'll elaborate that on a little more momentarily, although it's not going to be, I mean, this is not a course in quantum physics, so I'm not going to be like incredibly precise. And so the equation is the following. It's a linear partial differential equation, which is given by, well, I have minus I, where I is the complex number, I squared is -1, times the t derivative of u is equal to some number h with a slash through it is the normal notation over 2m times the second derivative of u with respect to x, right? And so this is what's called the free linear Schrodinger equation. So what does the m represent? This is the mass, so of mass m, right? So m is like the mass of your particle. And so this should look very similar to the diffusion equation, right? I have time derivative on the left-hand side, and this is equal to some constant multiple of the second derivative with respect to x. However, it's not quite the diffusion equation because we have a complex number here, right? And so the fact that the complex number I is here will change the theory of the equation pretty significantly. And so, I mean, I think this is maybe a surprising fact when you first learn about partial differential equations, but if you have a PDE that looks very similar, but you change one of the terms a little bit, this can kind of dramatically affect the theory of the solutions, and it can dramatically change the theory. And so this is one example where that's the case, where just adding a complex number here will completely change what the solutions look like. I mean, the formulas will look kind of similar, but like in terms of like qualitative properties of how the solutions behave, it's very different between the Schrodinger equation and the diffusion equation. This should also, I mean, point out that maybe calling I the imaginary number is not really a great idea, because this is kind of a fundamental partial differential equation in modern physics, and the imaginary number appears. So maybe this is not so imaginary, right? Because it's being used to describe something real, at least at the best that we understand it. Right, and so what is this number h? So this number h is Planck's constant from physics. And so I mean, I'm not going to go too much into detail about this, but basically like the energy, how is this number determined? Well, the energy is basically equal to this constant times the frequency of the particle. Right. So this means like the energy of the particle, and this is like the frequency of the particle. So what do we mean by the frequency of a particle? Well, one of the kind of sort of axioms, but there's experimental evidence for it also at the base of quantum mechanics, is that if you look at atomic particles, you can describe them either as particles or as waves, right? There's this wave-particle duality. And so this is like the frequency of the particle in the wave description, right? So the wave oscillates at some frequency, and so that's what we mean here. Right, but for the purpose of like the mathematical analysis of these equations, it helps to simplify this a little bit, so we don't have to deal with writing these h's and m's all over the place. And so what we're gonna do is, for simplicity, we're gonna set these both equal to 1. Right, so we're gonna set h equal m equal 1. This is not physically a valid thing to do, but mathematically it doesn't change the theory that we're going to develop. And so if you're interested in the physics, you can take everything that we did, that we're going to do for the rest of the lecture, and just repeat all the same arguments with the actual values of h and m, and you'll be able to get a formula that is maybe more physically valid. Right. Okay. Of course, the mathematical theory is the same, because mathematically these are just constants, which we can just ignore because we're more interested in the behavior of the partial differential equations. Constants are not a big deal. Okay. Okay, and so I do want to, I mean, this is not a physics class, but I do want to quickly, this may be familiar for some people, it may not be familiar for other people. I just want to briefly review kind of the interpretation of this equation or of the solution. Right, so the solution u of xt is usually referred to as like a wave function. Right, because even though it's supposed to be describing the motion of a particle, we have this wave-particle duality in quantum mechanics, and so this is kind of like describing the position of the wave, right? So this is describing the position of a quantum particle at time t. And so the sense in which it describes the position is a little complicated, but I'll talk about it. I'll sort of summarize the main points now. And so what we're going to do is let's assume that that if I look at the integral from minus infinity to infinity, that the integral of absolute value of u of xt squared dx is equal to 1 for all t. We're going to see that this is, I mean, you may think, how can you make this work? Because, I mean, sure, you can, if you fix t, you can multiply the function u so that this integral is equal to 1, right, by some constant. But as t varies, how do you know that it's going to stay equal to 1? Well, we'll see as soon as we look at how to solve the equation that this is actually not a strong assumption, and it's easy to assume that your solution has this property. Right, and so with this assumption, then the function u of xt describes, as I just said a minute ago, this describes the position of the particle at time t. It doesn't describe it in like the classical sense in mechanics. It describes it in a probabilistic sense, right? So in terms of probabilities. Right, and so in particular, the probability that the particle is in a particular interval, right, say is in interval between a and b, where a and b are just two numbers. So this is given by the integral from a to b of u of xt squared dx, right? And so this is at time t, right? And so why are we assuming this hypothesis about the integral of u squared being equal to 1? Well, this is going to be under this interpretation, this is just the probability that the particle is somewhere, right? So there's some position x where the particle is, right? And so we want the probability to be, we want there to be 100% chance that it's somewhere, or else the model, the particle's not going to just disappear, right? So this doesn't make, we want this to make some physical sense. And so that's kind of the reason for this hypothesis. And then, right, with this understood, then the probability that the particle is in a certain interval is given by the integral from over that interval of the solution squared, right? And so if you're familiar with probability theory, what we're really saying is that the solution squared is a probability density function, which describes like the odds of the particle being in a certain place, right? If you're not familiar with probability theory, that's okay. I'm not going to be testing you about anything related to probability. Right. Okay, and so this is just the, right, so this is kind of the behavior of, sorry, this is what the solution represents as a function of x and t in terms of probabilities. And so it turns out that if you take the Fourier transform, right, so let me introduce some notation. So I'm going to let u hat of ct be the Fourier transform of u of xt as a function of x at time t. Right, so this means that u hat of ct is given by integral minus infinity to infinity of u of xt e to the minus ixc dx, right? So u is a function of x and t. When I write this, I just mean take the Fourier transform in x, right, and let t vary, right? So this is what this means. Well, it turns out that this Fourier transform also has a physical interpretation in quantum mechanics. And so if you look at u hat ct and you multiply it by 1 over square root of 2 pi, well, this will describe the momentum of the particle in an analogous probabilistic way, right? So this describes momentum of your particle at time t. And again, it's going to be described in a probabilistic way. So the probability that the momentum is in interval between a and b is given by the integral from a to b of this object squared, right? So of 1 over 2 pi times Fourier transform with respect to x squared dc, right? And so, right, so in summary, well, the solution to the Schrodinger equation is kind of like, usually called the wave function, and it doesn't describe exact behavior of the particle like it would in classical mechanics. Instead, it describes the particle in a probabilistic sense, meaning like if you want to know the probability your particle is in a certain interval, you have to calculate the integral of the solution squared, and it will give the probability. And similarly, if you want to know the probability that the momentum of your particle is in a certain region, you have to integrate the Fourier transform of the solution times 1 over 2 pi squared, right? Fourier transform squared times 1 over 2 pi, right? Right, and so I mean, so this is kind of like the major change in quantum physics, which is, right, the solutions, or sorry, the physical behavior is no longer as deterministic as it is in classical mechanics, at least to the extent that we understand it. So we understand it in terms of probabilities rather than deterministic things. And so this is reflected by the fact that the solution to the partial differential equation describes probabilities in this way. It doesn't exactly describe what's going on. Okay, and so this was maybe a review for you. Sorry about maybe making this a little bit long-winded, but hopefully if you haven't seen this before, or you haven't thought about it in a while, this at least gives you some intuition about what's going on when we talk about solution to this equation. Right. Okay, and so now we want to actually move on and talk about like how are you going to solve this equation, right? So we want to talk about solutions. Right, so solving the Schrodinger equation using the Fourier transform. I mean, we already saw from the physical perspective that the Fourier transform is relevant for the theory of the solution, because if you have the solution and you transform it, you get something that gives you information about momentum. Right, and so, right, so as I said before, we're gonna set the Planck's constant equal to 1, and we're gonna set the mass of the particle equal to 1. Of course, in reality, neither of these are 1. They're both very small numbers, but again, we just want to talk about how you would solve an equation like the Schrodinger equation. And so in this case, the PDE becomes, well, I have minus I ut is equal to 1/2 uxx. And well, if I multiply by minus I get ut is equal to, or sorry, divide by minus I get ut is equal to minus 1 over 2I uxx. Well, this is the same as, well, if I multiply the right-hand side by I divided by I, right? So I'm gonna get minus I on the top. In the denominator, I'll get 2 times I squared, which is minus 2. And so those minus signs will cancel, and so I'll get I over 2 times uxx, right? And so this is the form that we're gonna look at the equation in. All this is just some algebraic manipulations, but it maybe simplifies it a little bit. And we're going to consider the initial value problem associated to this equation. So we want to look at ut is equal to I over 2 uxx with, right, so x is going to be between minus infinity and infinity. T is going to be bigger than or bigger than 0. And we want some initial state, say u of x0 is equal to some function c of x, right? So this is like your initial state. Right? And so in terms of physics, this function is also going to be interpreted in terms of probabilities, right? So this is like the initial position of your particle, but there's still some probabilistic interpretation, like, so this, like, right, in the sense described above, right? Okay, and so how are we going to solve this equation? Well, we're going to do the same exact argument essentially that we did for for Laplace's equation in the upper half plane. And so the idea is, well, take the Fourier transform of the equation in the x variable. Right, and so we're going to use the fact that the Fourier transform in x will turn x derivatives into some polynomial in the frequency xc, right? And so in particular, what do we end up with if we transform this equation? Well, we have on the left-hand side, we have some derivative with respect to t. This stays the same because we're not taking the Fourier transform with respect to t, we're taking it with respect to x. And so we have u hat of ct, right? This is on the left-hand side. And again, this is interpreted in the sense I talked about up here, right? So u hat of ct is the Fourier transform in x, right? And so that's on the left-hand side. On the right-hand side, well, I have some constant multiple I over 2, which will factor out, right? Because you can factor constants out of the Fourier transform. And then I'm taking the Fourier transform of the second derivative with respect to x of u. But remember, second derivative will become I times c squared when I look at the Fourier transform, right? So it transforms into I c squared times the Fourier transform of u, x, c, and t. Right. Again, this is the reason why the Fourier transform is so powerful for this type of problem, because I've turned two derivatives into just a polynomial coefficient, right? And then on the left-hand side, I have derivative with respect to t. Right, and so now this will simplify a little bit. So we end up with derivative with respect to t of u hat of ct is equal to, well, I squared is -1, so I get minus I over 2 c squared times u hat of ct, right? And so we're not quite done, but we're almost done, because what we have here is just an ordinary differential equation in the t variable, right? I have some time derivative on the left-hand side of a function is equal to some multiple of the function, right? And so this says that if I look at the function, say, let me define f of t equals u hat of ct, where c is fixed. This solves the ODE f prime of t is equal to minus I over 2 c squared times f of t, right? So technically, c is a variable, right? C can change, but let's just fix it and only look at this as a function of t. And so we're fixing c momentarily and pretending that it's not changing. In that case, we arrive at this ordinary differential equation, which we can solve relatively easily. Right, so this has the solution. Well, what do we have here? It says the derivative of f is a multiple of f. The only way that can happen is if f is exponential, right? It's the general solution. Well, we can solve this with f of t is equal to e to the minus I over 2 c squared t, right? Times some constant, right? Well, we have to be a little careful here, right? So this is a is constant in t with respect to t, right? Because we're taking antiderivatives with respect to t to solve this differential equation. However, it is possible that a could depend on c, right? Right. So we could have, and it will turn out to be the case that a will depend on c. right? So really A is a function of C, but it doesn't depend on T. That's the main point, right? And so while plugging this in, this tells us that the Fourier transform of our solution has to equal some A of C times e to the minus I over 2 C squared T, right? And so, well, how are we going to determine what A has to be? Well, we're going to use the initial condition here, right? And so we know we have information about when T is equal to 0, and so this will allow us to solve for A, right? And so we'll note that what happens if I set T equals 0 here, right? The reason why we're looking at T equals 0 is because when T is equal to 0, the exponential term will vanish, and so we can hopefully solve for A, right? Right. So, well, if I set T equals 0, U hat of C is the Fourier transform of U of x0 with respect to x. Right, because if I go back into the formula I have for U hat of CT, it's this formula here, right? And so if I set T equals 0, then T equals 0 inside the integral, and this is just the Fourier transform of U of x comma 0. But when T is equal to 0, U of x comma 0 is equal to the initial condition C, right? So this is the Fourier transform of C of x with respect to x. And so this tells me that U hat of C comma 0 has to equal the Fourier transform of the initial state C, right? But now I know what A has to be, right? So I know that U hat of C0 is equal to A of C times e to the minus I over 2 C squared times 0, which is e to the 0, which is 1. So this is A of C. And so these have to be equal, right? Because they're both equal to the same thing, right? And so therefore, the Fourier transform of the solution with respect to x is given by Fourier transform of the initial position function C times e to the minus I over 2 C squared T. Right? Okay, this tells us what the Fourier transform of our solution has to be as a function of Fourier transform with respect to x. But we have the Fourier inversion formula, which will now tell us what the original U of xt has to be, right? So by the Fourier inversion, well, U of xt has to equal 1 over 2 pi times integral from minus infinity to infinity of its Fourier transform times e to the I xc dxc. Right, and so if I plug in what we just obtained, we get U of xt is equal to 1 over 2 pi times integral from minus infinity to infinity of Fourier transform of the initial state C times e to the minus I over 2 C squared T times e to the I xc dxc. Right, so this is our solution formula for the Schrodinger equation. For the initial value problem associated to the Schrodinger equation, right? Right, and so you may wonder, like, okay, this formula involves the Fourier transform of the initial position function. Is it possible, like we did for the Laplace equation, to get a formula that involves not C hat here, but C of x? So it turns out that there is a way to do this, although the proof of this will require some integration techniques from complex variables or complex analysis. So we're not going to do that in this class, but the formula does exist. And you can actually just, if you look in the textbook and the section in chapter 9 that's devoted to the Schrodinger equation, it's just written down in the corresponding formula in terms of the spatial variables C of x, right? So if you're interested, you can find that there as well. Right. Okay, and so in the final part of the lecture, I just want to talk about some properties of the solution and some related things, and then we'll be done. Right. So one immediate consequence is conservation of mass, which has physical importance. Right. So this is the conservation of mass. And so the theorem is the following. So let me define the mass of the solution to be the integral from minus infinity to infinity of u of xt squared dx. Right. So this is kind of like this is the same quantity as like the total probability that the particle is somewhere, but this also has the interpretation as the mass. Well, the theorem is that if I look at this integral, right, so this is the mass at time t. Well, this is actually equal to the integral of u of x0 squared. Right, so this is the integral from minus infinity to infinity of the initial state, say c squared. Right, and so this means that this quantity, the mass, is conserved over all time. Right, so for all time, this integral is always equal to the integral of the initial position squared. Right, and so in particular, if we choose our initial position such that the integral of c squared is equal to 1, this is true for the solution for all time. Right, and so this justifies what I mentioned earlier in the lecture, which is, well, in order to have this probabilistic interpretation of the solution, we need to assume that this integral is equal to 1 for all t. Well, how can you get this to work? Well, you just assume that it's true for the initial position function c. And once it's true for this function, which you can assume by multiplying this function by some constant to make the integral equal to 1, it's true for the solution for all time. Right, so this is one reason why this theorem is important. Right. And so the proof is a relatively easy application of Plancherel's theorem as long as you understand the Plancherel theorem. And so the proof is the following. Well, let's look at the integral from minus infinity to infinity of u of xt squared dx. What we're going to do is apply the Plancherel theorem from the last lecture in the x variable. Right? So Plancherel theorem says that if I look at the integral of a absolute value of function squared, this is equal to the integral of the absolute value of its Fourier transform squared times 1 over 2 pi, right? And so by the Plancherel theorem, this is 1 over 2 pi integral from minus infinity to infinity of the Fourier transform with respect to x with t fixed, right? But now we have a formula for u hat of ct. It's the first formula we found up here, right? So I'm going to plug this in. Right, so now this is equal to 1 over 2 pi times integral from minus infinity to infinity of absolute value of Fourier transform of c at c times e to the minus I over 2 c squared t squared. Right? But if I look at the absolute value of a complex exponential, for the first thing to point out is that if you look at the absolute value of a product of two functions, this is the same thing as the product of the absolute values, right? But then absolute value of a complex exponential like this is just 1, right? So this is 1, right? Because remember, the complex exponentials lie on the unit circle in the complex plane, and so their length is always 1, as we saw several weeks ago. And so this is just equal to 1 over 2 pi times integral from minus infinity to infinity of absolute value of the Fourier transform of c squared. Right? But now we're going to apply the Plancherel theorem again, right? So by using Plancherel again in x, this is equal to now integral from minus infinity to infinity of c of x squared dx, right? And so that's what we wanted to prove, right? At every step here, we had an equality, and so the first thing we started with is equal to the second thing, and this is exactly what's claimed up here. Right? Okay, so that's the conservation of mass associated to the Schrodinger equation. The final thing I want to discuss, which is related to Schrodinger equation and also kind of more generally just related to the Fourier transform, is the uncertainty principle from physics, which is kind of a famous application of the Fourier transform. Right. Okay, and so the first thing I'm going to do is just state an inequality, and then I'll elaborate on it a little bit and talk about how it relates to what we've been discussing so far. And so we're going to assume that, right, so we'll have some u of xt, which you want to think of as a solution to the Schrodinger equation from before, although this, what I'm going to write down actually holds more generally for more general functions, but for this lecture, maybe just pretend it, or just think of it as the solution to a Schrodinger equation. Right, so we're going to suppose now that the integral from minus infinity to infinity of u of xt squared dx is equal to 1 for all t, which we can assume as for at least for the Schrodinger equation, as we saw above, just by scaling the initial position function. Right, and so the statement is of the uncertainty principle is the following. So if we look at the integral from minus infinity to infinity of x minus x naught times absolute value of u of xt squared. So x naught will just be some arbitrary point, integrate with respect to x. And we multiply this by a similar integral in terms of the frequencies. So now I have, oh, this should be squared, sorry. Xc minus some xc naught squared times u hat of xt. Once again, this is the Fourier transform only in the x variable, right? So the conclusion is that if I multiply these two things together, this is always bigger than or equal to 1/2, no matter what, right? For all t and any u as above. Right? And so, right, so for here we wanted to fix, fixed points x naught, c naught. So these are like some say fixed positions and momentums. Right? Okay, and so the last thing we're going to do for the lecture today is prove this. But first, I want to discuss a little bit of like the interpretation, right? So here we fixed a particular position x naught and a particular frequency, which we want to think of as momentum c naught. And so what we have here is something, two quantities which measure kind of the uncertainty that the particle is at position x naught and at momentum c naught, right? And so the left term here measures the uncertainty that your particle is at position x naught at time t. And so this quantity over here measures the uncertainty that particle is at momentum or has momentum c naught. At time t, right? And so, well, why do these things represent uncertainties? In order to more precisely talk about this, we do need to use some stuff from probability theory, which I'm not going to assume that you have experience with. But if you do have experience with probability theory, so remember we mentioned before that the absolute value of the solution squared is the probability density function for the position of your particle. And similarly, the absolute value of the Fourier transform squared is probability density function for the momentum of your particle, both of which are interpreted as like random variables, right? So you don't know precisely where they are. They have a random variable interpretation. And so what we have here is just the variance, assuming that x naught is like the mean or something like that, right? And so these two quantities measure the variance from a particular point. And so this is kind of like a measure of uncertainty. Like we don't know precisely. Right, so sorry, we're measuring the extent to which the solution can vary from what's expected, right? So this is the idea. And so here is the variance for the position, and here's the variance for the momentum. And so these have the interpretation of uncertainties, right? So for example, if the uncertainty is high, it means we're not sure that the particle will be where we think it should be. And similarly, if the uncertainty over here is large, then it means that the particle has a high chance of not being where we expect it to. The momentum has a high chance of not being where we expect it to be, right? Okay, and so why is this, like, what does this have to do with what you may know as the uncertainty principle? So notice, what does this kind of say? This says that if you look at, oh, sorry, I forgot to, right, I should have had a 1/2 pi in here, right? Because remember the momentum involved a 1/2 pi, sorry about that. Okay, but anyway, so moving on, what does this actually say? Well, the term on the left is like the uncertainty in position. Term on the right is, the second term on the left is the uncertainty in momentum. And this inequality says that the product of these two quantities always has to be bigger than or equal to 1/2, right? And so this says that they can't both be small. Right, so in particular, let's say we're pretty sure where the position of the particle is, right? So if we're pretty sure about the position of the particle, right? So maybe then the uncertainty is very small, like maybe like 1/1,000,000, right? Or let's say 1/100,000. Right, so let's say very small uncertainty for position. Well, that means that this is true no matter what, right? This inequality, which is what we're stating over here, although we haven't proved it yet. So that means that the uncertainty in momentum has to be large to make up for this, right? So that means that the uncertainty in momentum would have to be 1/2 times 100,000, right? Otherwise, this inequality would fail, right? So this needs to be at least this much, right? So kind of loosely speaking, this says that if we're pretty sure about the position, then we don't know anything about the momentum, right? Or we can't be sure about the momentum. Right, and so this means that if you have low uncertainty in say the position, there has to be high uncertainty for the momentum. Or similarly, if you have low uncertainty for the momentum, then there has to be high uncertainty for the position, right? And so in particular, you can't know with high precision both the position and the momentum of your particle, of the quantum particle, right? So there's always going to be some, if you know one very well, there's some uncertainty about the other. This is what this means. Okay, and so how would you actually prove this? So it's going to be, it turns out that at least for this, sorry, it's going to turn out that it's just going to be kind of an exercise in integration by parts and the Cauchy-Schwarz inequality, which we have seen a few times. Right, sorry, I just wanted to mention that, remember at the beginning of this discussion, we assumed that Planck's constant was equal to 1. So in reality, this is really going to be Planck's constant over 2 or something like that, right? It's going to be scaled by the Planck's constant, right? So you may think, well, this is pretty large, so maybe, so what's going on here? Like, I mean, this means that we sort of can never understand sort of what's going on, right? If there's always like some very large uncertainty, like 1/2 seems like a pretty big number in terms of probabilities. Well, it's really like actually a very, very small number, right? So this Planck's constant is a very tiny number. And so, I mean, this says you always, if you know one of these two very well, there's still going to be some uncertainty in the other, but it's not quite on the order of magnitude of 1/2 in the real world. It's really some smaller number. I just wanted to point that out. Okay, and then, so let's finish the lecture then with a proof of this inequality. Right, and so the idea is, well, let's look at the integral from -infinity to infinity of a certain augmented function. Well, what we're going to do first actually is assume that x0 is 0 and x0 is 0. The more general case is similar, but I'm not going to prove that here. Right, and so the idea is, well, let's come back to this expression here. So notice that here I have c squared, right? C0 is 0 now, times Fourier transform of u squared, right? But remember that a polynomial multiple of the Fourier transform, like c squared times u hat squared, this should remind you of like derivatives of u, right? Because polynomial multiples of on the Fourier side is equivalent to derivatives on the x side or the spatial side. And so the derivative of u should be relevant. And so to take advantage of this, we're going to look at the integral from -infinity to infinity of a certain related quantity. It's going to be x times u of xt times x derivative of u at xt. Right? So we'll see why we're doing this in a second. So what I'm going to do is apply the Cauchy-Schwarz inequality. Right, so this is less than or equal to integral -infinity to infinity absolute value of x times absolute value of u of xt times absolute value of ux of xt dx. And so by the Cauchy-Schwarz, which we proved on an earlier homework assignment, we proved it on a finite interval, but the proof is the same on an infinite interval. So it's same thing. So this is less than or equal to, well, we're going to apply it with, this is one of our functions f, and this is another function g. Cauchy-Schwarz says that integral of f times g is less than or equal to integral of f squared to the 1/2 times integral of g squared to the 1/2. Right? And so with this in mind, well, we get that this is less than or equal to integral from -infinity to infinity of x squared times absolute value of u of xt squared to the 1/2 times integral from -infinity to infinity absolute value of ux of xt squared dx to the 1/2. Right? And well, this term here is exactly what we have in our inequality with x not equal to 0. And then, well, the second term, we're going to be able to convert it to this using Plancherel's theorem, right? So notice that if I take the Fourier transform of ux, this is just equal to I times xi times u hat, right? So this is one of the key properties of the Fourier transform. And so by Plancherel's theorem, if I look at, oh, sorry, this should have been an x, excuse me. If I look at the Fourier transform, or sorry, if I look at the integral of u sub x derivative of u squared, this is equal to 1/2 pi times the integral of its Fourier transform squared. Right, so this is just Plancherel. And so this is equal to 1 over 2 pi times integral from minus infinity to infinity of c squared, because absolute value of I is 1, times absolute value of u hat squared with respect to c, right? And so if I plug this formula into this quantity here, we get exactly the one side of our inequality, right? And so this is equal to integral minus infinity to infinity of c squared times u hat squared, right? And so it remains to, so this is the left side of our inequality here. And so all we have to do is show that this integral that we started with is bigger than or equal to 1/2, right? So we want to show this is bigger than or equal to 1/2. Because once we do this, we'll be done, right? Because on the left-hand side, I have 1/2 is less than or equal to this integral. And then this integral is less than or equal to the uncertainty in x times the uncertainty in c, right? Or uncertainty in position times the uncertainty in momentum. Oh, sorry, there's a 1 over 2 pi here, excuse me. Right. Okay, and so finally, just to show this last bit, we just have to integrate by parts. And so we're looking at the integral from minus infinity to infinity of x times u of xt times ux xt dx, right? Well, notice I can write this as integral from minus infinity to infinity of x times derivative with respect to x of u squared times 1/2, right? Right, because if I differentiate u squared, I get 2 times u times ux, right? And so here I have u times ux, which is why the 1/2 is here, right? Just to, right? And so this is equal to 1/2 times integral from minus infinity to infinity of x times the derivative of u, right? And so now we're just going to evaluate this by integrating by parts. So this ends up being well, we have the boundary terms, which end up being 1/2 x times u squared evaluated between minus infinity to infinity. And then we have minus integral minus infinity to infinity 1/2 times u squared. Right. Right, and so, well, we need to add an additional assumption, I guess, here. So, well, we know that the integral of u squared is finite from minus infinity to infinity, and so that means that u has to decay at infinity. And so the additional assumption will be that, well, let's assume that u decays fast enough that x times u squared is also going to decay, right? So we're gonna, well, then in this case, this is gonna be 0, since the limit at plus or minus infinity is 0. Under suitable hypotheses, right? And so then we're just left with minus 1/2 times the integral of u squared, right? And so we're assuming that the integral of u squared is equal to 1. So this is equal to minus 1/2, right? But then if I take the absolute value, well, then this is equal to the absolute value of this, which is absolute value of 1/2, which is 1/2. And so then indeed, this is actually not just bigger than or equal to 1/2, it's actually equal to 1/2. Right? Right, so there's a minor error here, which you may have noticed if you're paying attention, which is, well, u may be complex valued, and if you multiply a complex number by itself, that's not the same thing as the complex absolute value. So one way around this is to just assume that u is real valued, but you can also make the argument work if you don't assume that. But I'm not gonna. I think we're running out of time. It's best to just end now. Right. Okay, and so I mean, I guess I should have said this earlier, but I'm not gonna test you on the uncertainty principle, but I think it's helpful to see as an application of the theory of the Fourier transform, like kind of one version of this kind of famous principle from physics. Okay, and so that's it for now.